Hi, welcome to our lecture on electricity. This lecture will combine material from chapters 16 and 18 in your textbook. Part 1 of the lecture is an introduction to electricity and electric circuits. In part 2 of this lecture, we'll cover electric circuits in more detail using Ohm's law. So in order to understand the basics of electricity, we need to know a little bit about the atom. And this is something we're going to discuss in much greater detail later in the course when we have a whole chapter on atomic physics. But for right now, we can get by with just a very basic picture or model of the atom. The atom has a nucleus in the center that consists of protons and neutrons. The protons are positively charged particles, and the neutrons are neutral, meaning they do not have an electric charge. Around the nucleus is a cloud of negatively charged electrons. So atoms and materials made from atoms are typically neutral. That means that the same number of electrons as protons, because these charges will cancel each other. So the main, most fundamental concept of electricity is the concept of electric charge. Electric charge is a property of matter due to electrons and/or protons, and it's responsible for all electric and magnetic phenomena. So we saw in the last slide that electrons have a negative charge and protons have a positive charge. This is where electricity comes from, this electric charge from these particles. Electric charge is abbreviated with the letter Q, and it is measured in units of coulombs, named after a French physicist, Coulomb. And the abbreviation for coulomb is a C. So for example, positive charge in nature is due to protons, because remember, they are positively charged particles. And the positive charge of a proton, Q, is equal to 1.6 times 10 to the minus 19 coulombs. So this is obviously a very small amount of charge, because we're just talking about a single proton that sits inside the nucleus of an atom. Negative charge is due to electrons. And the negative charge of an electron is equal to the same amount as the proton, but it has a minus sign in front. So there are two types of charges, and we call them negative and positive charges. But you can see that the electron has a charge of negative 1.6 times 10 to the minus 19 coulombs. And then once again, the neutrons, the third type of particle in an atom, has no charge. They are neutral. That's where the name neutron comes from. So their Q, or charge, is equal to 0. One of the fundamental properties of electric charges is the existence of an electric force. And this is sometimes called the Coulomb force. And it's described by what is called Coulomb's law. It's the force between two electric charges. And the force is proportional to the product of the two charges, Q1 and Q2, divided by the square of the distance between them. That's what R is. So F is the force between two charges. The main things here are that the charge can either be repulsive or it can be attractive. So for like charges, meaning two of the same type of charges, the Coulomb force, or electric force, is repulsive. All right, so this means that two positive charges, if they're placed next to each other, they will be repelled by each other and push away from each other. The same thing happens if we have two negative charges. They will also be repelled from each other. You've probably heard the saying that opposites attract. Well, that comes from electricity. Opposite charges have an attractive force, so a positive and a negative charge will have a force, given by this law up here, but the force is attractive, which will tend to pull these two charges together. At this time, let's watch a video demonstration of something called a Van de Graaff generator that basically builds up charges by collecting electrons.
As you probably know, this is a Van de Graaff generator, and it's widely used in schools to demonstrate a range of electrostatic phenomena. Now, it can be quite tricky to get working, and I'll give you a couple of tips on that in a minute. But for now, let's just switch it off, discharge it, and take a look at how it works. The Van de Graaff generator is basically a device for moving electrons from down here to up here. Now, the electrons begin their journey on a piece of metal at the base called a cone. They're then carried on this moving belt to this sphere where they accumulate until the voltage becomes high enough to create a spark. They then travel to this secondary sphere, through the metal, through this wire, and back to the comb at the base. Now, this gap is approximately 4 centimeters, which means that in order to create a spark, the voltage between the spheres needs to exceed 100,000 volts. When I rub this balloon on my shirt, it becomes electrically charged. That's because there's a transfer of charge between the balloon and my shirt. Now, this occurs because the cotton in my shirt attracts electrons more strongly than the rubber in the balloon. And a similar process happens in the Van de Graaff generator. As the rubber belt approaches the plastic roller, the electrons in the rubber are attracted to the plastic roller. The material of the roller has been chosen especially to make this happen. This leaves the outer surface of the belt positively charged. As the belt travels round, it passes the lower comb, and electrons are attracted across the gap onto the belt. These electrons are then taken up on the belt to the upper sphere. Now, the electrons on the belt repel each other, but they're unable to move because of the insulating properties of the rubber and the insulating properties of the air. So let's see what happens when the electrons reach the upper dome. Here, the belt passes a second metal comb, which provides a conducting path for the electrons to leave the belt, travel through this wire, and spread out over the upper dome. Now, there have been a couple of subtleties about this explanation that I'd like to draw your attention to. The first concerns the contact between the rubber of the belt and the plastic of the roller. When I rub the balloon on my shirt, we cause charge transfer by friction between the two materials. Here, in the Van de Graaff generator, the charge transfer occurs simply by contact between the rubber of the belt and the plastic of the roller. The second point concerns the metal comb. The metal comb doesn't have to actually touch the rubber in order to provide a conducting path. Electrons are able to move across that gap quite easily. And the third point concerns the material of the rollers. The upper roller is made of a different type of plastic to the lower roller. It's been chosen to attract electrons less strongly than the material of the lower roller. And because of this, there's a net transfer of electrons from the lower part of the apparatus to the upper part of the apparatus. If the rollers were made of the same material, you can see by symmetry that there'd be no transfer of electrons. When Van de Graaff generators come out of storage, they frequently don't work very well at first, and the usual culprit for this is moisture. Moisture on the rubber belt provides conducting paths by which electrons can work their way back down to the base. Also, moisture in the air provides conducting paths through which electrons on the dome can leak away. So the cure for both of these is a hairdryer. Running a hairdryer over the belt of the Van de Graaff while it's working for about 5 minutes should cure both of those problems. If the Van de Graaff still doesn't produce good sparks, then it could be the insulating supports. If these have fingerprints on, then these also provide conducting paths by which the charge can leak away. Cleaning with isopropyl alcohol should cure that. If the Van de Graaff still isn't working, then it could be the belt. If the belt feels dry or brittle, then it's time to get a new belt. Now, before I show you my favorite demonstration, a word about safety. Despite the very high voltages that they generate, Van de Graaffs are surprisingly safe. That's because the amount of charge in each spark is really rather small. So for healthy people, there really is very little hazard. However, if there's somebody in your class that has a heart condition, then they should keep their distance from the machine. About 1 meter should be okay. Now, on with the demonstration. You can do all kinds of things with a Van de Graaff generator. You can make people's hair stand on end. You can light a Bunsen burner. You can pass electric charge along a whole line of small children. But I like this demonstration, which just involves some metal cake tins. Watch this. The Van de Graaff generator is charging the dome with electrons, and they spread out across the dome. Because the cake tins are metallic, the electrons also move onto the cake tins. The tins become negatively charged, and so they repel each other. The one at the top doesn't have the others weighing it down, and so as the charge builds up, eventually the repulsion becomes sufficient to push it off the pile and lift it into the air. Then the same thing happens to the one that's now on the top, and so on down the pile.
We saw in the video of the Van de Graaff machine that we can ionize something or charge it. And so the term ionization means charging by electrons added or removed from atoms. So for example, rubbing two different materials together or placing them in contact with each other can cause electrons to be transferred from one material to another. And you're probably familiar with this if you've ever, especially on a dry, hot day or winter day when there's not much humidity, if you rub your shoes, your tennis shoes, for example, on carpet, you'll build up a charge on your body, and when you touch another person or maybe touch something large and metal like a metal door or something, you'll feel the shock and maybe even see the spark. So this is due to ionization. So what's happening here is, remember, an atom is normally neutral, meaning it has the same number of positive charges in here as it does negative charges. So in this example, let's say we have an atom with 5 protons, so we have 5 positive charges. Well, normally there would be 5 electrons, but you can see that this atom only has 4 electrons, here, 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 and here. So what happened to the 5th electron? Well, that 5th electron was actually transferred over to this atom here. You can see this one now has an extra. It has actually 6 electrons instead of 5. So both of these are ions. This is a positive ion because it has more positive charge than negative charge, and then this is a negative ion because it has picked up an extra electron and has more negative charge. If you take a balloon and rub it against, for example, if you're wearing a sweater or maybe a flannel shirt, or even rub it against your hair, you can transfer charge between your body and the balloon, and when you charge up this balloon, you can stick it to a wall and it'll actually stick because of those charges transferring there. Another one is you can take a comb and comb your hair, especially if you have long hair, and you can actually charge up the comb to the point where you can actually pick up pieces of paper on the table due to the attractive force between positive and negative charges. Electrical storms and thunderstorms are great examples of electricity in nature at a grand scale. So what happens is inside of storm clouds, charge separation occurs, and this is due to a combination of friction between the cloud molecules and also the formation of raindrops tends to separate the charge so that the top of the clouds are typically positively charged and the bottoms of the clouds are negatively charged, meaning they have extra electrons down here. So what can happen here is the bottom of the cloud, which is negative, will attract positive charges in the Earth. Basically, the way it does this is it actually repels electrons away from these atoms, leaving positive charges behind. When there's enough voltage between the bottom of the cloud here and the Earth below, lightning will occur such that that charge can transfer through the lightning bolt. There's also, so that's cloud to ground lightning. There's also cloud to cloud lightning. You can see the negative part of this cloud here. We can have a lightning bolt going over to a positive part in the cloud next to it. One of the other fun demonstrations with the Van de Graaff generator is with hair. And remember, the idea here is that when you touch this Van de Graaff generator, which is full of charge, all right, let's just say it's negative charge, full of electrons. Well, then when you touch that, those electrons flow into your body and you become charged. So all your hairs on your head, actually everywhere on your body, they all become negatively charged. And remember that negative charges repel other negative charges, right? Remember that like charges repel each other. They don't attract. So all of your hairs now are trying to repel or get away from each other. And the best way they can do that is by moving straight up and as far apart as they can from each other. So this makes your hair literally stand up. So enjoy the video demonstration of the Van de Graaff generator with hair-raising experiences.
Welcome to the Museum of Science and Energy. My name's Miss Wright, and we're very glad to have you here today. We'd love to invite people into our auditorium to try out the Van de Graaff generator. If you're not real familiar with Van de Graaffs, they produce static electricity. They do a little bit something unusual to your appearance when you try them out. You could actually pull the top off of the Van de Graaff and look inside. What you would see is a roller at the top, one at the bottom, and a belt that sits on those two rollers. When we turn the motor on, that belt starts to spin really fast, and as it spins, there's a little metal comb that strips away electrons. So the Van de Graaff builds up a very strong positive charge. When we have a volunteer stand on our insulator, they put their hand on the Van de Graaff. It steals some of their electrons and makes them a very positive person. All of those positive charges build up in their hair and they start to repel, similar to magnets.
It was very shocking and weird. I've never felt anything like it before, and you should come out to AMZ to try it.
This is Miss Wright at the American Museum of Science and Energy. If you would like to try the Van de Graaff, come and join us in Oak Ridge at the museum or check out our website at amsc.org.
One of the basic concepts of electricity that is very important, particularly for the application of electric circuits and electronics, is the idea of electric current. So what is electric current? Current is the rate of flow of electric charge, and current is given the letter I. So I is equal to the amount of electric charge that flows divided by the amount of time it takes to flow. All right, so it's the rate of flow of charge. So remember, charge, we can abbreviate that with Q, and time, of course, is we can abbreviate that with T. So I is equal to Q over T. Now the units of current, up here we have charge, which is measured in coulombs, and down on the bottom we have time, which is measured in seconds. So current is measured in coulombs per second. Because current is such an important parameter and concept in electricity, we give current its own unit. A coulomb per second is called an ampere. And an ampere is named after Andre Ampere, a French physicist who studied electricity. It's abbreviated with the letter A, and sometimes an ampere is abbreviated by just saying amp. So for example, a 2 amp fuse means a fuse that is rated at 2 amperes of current. So it's useful to think about current with an analogy. If you think of a river current is basically the flow of water. So we have water flowing down this river. Well, electric current is sort of similar. It's the flow of electric charge. So here we have a wire, and what's shown inside the wire are the electrons flowing through the wire. And so this is our idea of what electric current is in a wire. It's electrons flowing through the wire. Now, one thing that's a little bit confusing about electricity and electric current is that, remember, electrons are negatively charged. So the electrons are flowing to the right. So that is a negative current flowing to the right. Because we usually don't want to deal with negative quantities, let's call the current positive, but positive current is flowing in the opposite direction to the left. So this is sometimes called conventional current, is flowing in the opposite direction as electrons because we like to deal with the positive value of current. Here's an example to calculate current. 3 coulombs of charge flow through a wire every 6 seconds. How much current is there? So we know that I, current, is equal to Q over T. Q is 3 coulombs, and that takes 6 seconds to flow through the wire. So 3 divided by 6 is 1/2, which is 0.5 coulombs per second, or we say 0.5 amperes, or 0.5 amps. It's useful in some of the topics that we're going to be talking about in this chapter and the next to think about what electricity is like down at the microscopic or atomic level. And for this, we're going to talk about 2 types of materials that are important for electricity, that is conductors and insulators. So a conductor is a material with lots of loose charges available to flow. And examples of good conductors of electricity are metals. So this is an atomic model of a piece of metal. We've seen something like this earlier in the course where we had all these metal atoms connected together by bonds. Okay, so this is a solid piece of metal. What happens in the solid here is that some of the electrons that are normally attached to these atoms are very loosely held. In fact, they become free to move around inside of this conductor. So in this metal solid here, we have a whole bunch of what they call free electrons, all right, meaning they're not bound to these atoms anymore. They're free to roam around. This is also sometimes called a sea of electrons. You can almost think of these electrons as a fluid or a gas that can flow inside of this metal, especially now when we're going to hook up this piece of metal, which might be a wire. If we hook it up to a battery, that's going to cause these electrons to flow through the conductor, which creates a current. And that is exactly what electric current is. It's the movement of these free electrons, or the sea of electrons, flowing through the conductor. Sort of the opposite of a conductor is an insulator. An insulator is a material that has no loose charges, so no current can flow. So examples of insulators are plastic, glass, and rubber. Wood is also a pretty decent insulator. So if we look at the same type of model for an insulator, again, we have all the fixed atoms. So, you know, if this is glass, These would be glass atoms or molecules. Glass is silicon dioxide. But the key thing here is we've got all these atoms, but notice there are no loose electrons. There are no free electrons. There's no sea of electrons. So where are all the electrons? Well, they're actually bound to these atoms. They're tightly bound to these atoms. They can't free themselves and move around inside. So an insulator has no free electrons to move, therefore current can't flow through an insulator. We can now start to talk about and imagine or model a very important part of the study of electricity, and that is the idea of an electric circuit. So before we actually talk about electricity flowing through wires with batteries and so forth, let's do an analogy here that'll make it much easier to envision of what's going on in an actual electric circuit. Electric circuits are similar to moving water through pipes using a pump. So in this system here, we have a water pump, and the pump is connected to a tube or hose that just goes around in a circle like this. And this is why it's called a circuit. Okay, it actually forms a loop here. The way the pump works is it creates high pressure on one end of the pump that pushes the water in this direction. Now remember, the flowing water makes a current. So this is not electric current, obviously, this is water current, but it's the same kind of idea. The water then flows through here, and notice here the pipe or the tube becomes narrower. And so it's harder to squeeze the water through this narrow part of the pipe. So this creates some resistance to the flow of the water. So this is what we call a resistance here. And then the water returns and it comes into this end of the pump, which is at low pressure. So notice the water is just circulating through around and around this circuit. Okay, it's the same water being used over and over and over. One thing we can also see here, which is going to also be the case for electricity, is that the same amount of current must flow through each part of the loop. That means the current right here is the same as the current here, because this current is continuous. It can't build up or it can't leave the system. So it has to, if we have 2 gallons per minute flowing up here, we have to have 2 gallons per minute flowing through here, and we have to have 2 gallons per minute flowing down here, and also we have 2 gallons per minute flowing through the pump. So this is one of the key things about a circuit like this, is that wherever we look at the current, it's identical. The same amount of flow must occur everywhere. So now let's take our water circuit with a pump, and let's see how this transfers over to electricity. So in an electric circuit, we have electric charge, which is flowing through the wires, so that makes our electric current. And instead of a pump, we have a battery or a power supply, which causes the current to flow. So this looks very similar to the picture on the last page. Instead of a pump, we have a battery, and the battery produces high voltage on one end of the battery, that's the positive terminal, and low voltage on the other end. So there is a voltage difference across the battery that causes current or charges to flow. So the current flows, notice, from the positive post or terminal of the battery around through the circuit, and it comes back in at the negative terminal of the battery. So this is something we're always going to have to remember. Current goes from positive to negative. And in electricity, a resistance, which means something that makes it harder for the current to actually flow, is represented by this zigzag symbol here. This is the symbol for what is called a resistor or a resistance. And again, the same current flows up here as it does here and down here. Let's take a look at this idea of resistance in a little more detail. What is resistance? Well, resistance is the opposition to current flow. In other words, it resists the flow of current. So resistance is abbreviated with the letter R, and the unit of resistance is called the ohm, O-H-M, and the symbol for an ohm is the Greek letter omega, because omega sounds like ohm. This is the uppercase Greek omega, by the way. So the symbol in a diagram, or what's called a schematic diagram in electricity, for a resistance is that zigzag wire like this. So in this picture here, we see a resistance, and the value of the resistance R is 5 ohms. Now, what actually causes resistance? Well, it's the collisions between the electrons that are flowing and the atoms that are inside the wires. Kinetic energy from the electrons is transferred to the wire metal atoms. So in this picture here, this is a little section of a wire. Let's say it's a copper wire. So these red, big red circles here represent copper atoms that are bonded together to make a solid wire. You see the little tiny particles, those are electrons, and they're flowing from left to right. But notice the electrons can't just flow straight through, they bounce off and they collide with all these copper atoms. And even in the tiniest wire, there are trillions and trillions of copper atoms, and there are trillions and trillions of electrons. So there are a lot of tiny little collisions happening all the time when electricity current flows through a wire. Now what happens is, first of all, that since these electrons have to bounce off of all these copper atoms here, this is creating resistance. But furthermore, these copper atoms start to vibrate more because of all the collisions. And remember from earlier in the course, we talked about what thermal energy is. Thermal energy is the vibration of all the atoms in the substance. So what happens here as we pass current through a wire or a resistance like this, the wire can heat up. All right, we're basically taking kinetic energy from these electrons and we're transferring it to kinetic and potential energy of these atoms wiggling and jiggling around. We're basically transferring or converting to thermal energy. So this is how light bulbs, incandescent light bulbs like the type that Thomas Edison invented, toasters and hair dryers work. It uses this principle of taking electric energy due to these moving electrons and converting it into thermal energy where we have a lot of vibration of the atoms. So resistance converts electric energy into heat and light. So in this light bulb here, so this is the the old-fashioned incandescent type of light bulb. This is not an LED light bulb, and it's not a fluorescent light bulb. They work on a different principle. But the old-fashioned incandescent light bulb has what's called a filament, and you can see this little skinny little wire inside the light bulb, and when we pass electric current through it, the wire heats up. In fact, it heats up so much that it glows, and depending on how much current we put through there, it can glow very brightly to make an effective light bulb. A hair dryer. Inside the hair dryer, there are wires. You can see them wrapped around the heating element here, and when we pass electricity into these heating wires, they heat up and they glow and they become hot to create hot air. A toaster, if you've ever looked down inside of a toaster when it's actually turned on and toasting, you will see the wires in there glowing bright red. This is again due to electric current passing through those wires. This is an electric portable heater, like you might put in an attic or a garage or something like that. The same principle is applying here. We have wires with electricity running through them to heat up the wire. This is an electric stovetop. And again, you can see these wires or heating elements are glowing red because of the electricity passing through them. So there's a couple of demonstrations you can watch where we're converting electric energy into thermal energy. This one is shown here just in this little animation. It's a wooden pencil, and they sharpened both ends, and they connected it to some clamps here and connected it to some sort of power supply. And the electricity flows through the pencil lead, which is actually not lead. A pencil lead is made of graphite, which is carbon. And so as the current passes through there, you can see it heats up to the point where it actually burns away the whole pencil, and then the lead finally turns red hot at the end, and you can see it melt. You'll also next watch another video demonstration that someone did of melting wires, again, just by passing electric current through the wires. So enjoy this video too.
Bob, beautiful. The reflection is epic. We'll do that again. Burnt out.
So far in our discussion of electric circuits, we've talked about current, which is the flow of charge, and we've talked about resistance, which is the resistance to the current to flow. The third thing that we need to talk about is called voltage. And voltage, you can sort of think of it loosely as electrical pressure that causes current to flow. So remember, in our circuit diagram, instead of a pump to pump water, we put a battery to pump electricity or pump charge. And the way the battery does this is by creating a voltage. The battery has a voltage assigned to it. For example, your car battery is 12 volts. A AA battery or AAA battery that you might put in a remote control, that is 1.5 volts. But this voltage acts like an electrical pressure that pushes the electric charges and causes them to flow in the circuit. So voltage is measured in volts, and volts are abbreviated with the letter V. The more precise definition of voltage is how much energy in joules each charge has, or how much work each charge can do. So a volt is technically defined as a joule per coulomb. So it's sort of the amount of energy per charge. And this definition is it's an important definition in some more advanced physics classes, but we're not going to really deal with this definition in this class. For us to understand just the basics of electric circuits, it's easier to think of voltage as this electrical pressure that causes current to flow. So from our plumbing analogy, it's the pressure difference that causes water to flow. So it's the voltage difference that causes current to flow. So if we have a resistance here, so remember here's our symbol, this little jagged line stands for a resistance, R. And if we have one end of this resistance connected to a high voltage, for example, the positive terminal of a battery, and if we have the other end connected to a lower voltage, for example, the negative terminal of a battery, then we will have current flowing through the resistance, and that current is due to this voltage difference across the resistance. So this voltage, again, you can think of it kind of like pressure or almost like a force that's pushing the charge through this resistance. It's creating current to flow. And this is basically, this is the basic idea of how electric circuits work. Let's return just briefly back to our idea of lightning. Charge separation in thunderstorms. Remember the cloud and a thunder cloud, the top of the cloud is positively charged and the bottom of the cloud is negatively charged due to charge separation, when the raindrops are forming and friction within the cloud and so forth. But the voltage that is created by this charge separation can exceed 100 million volts, which is an incredibly high voltage. Remember, a battery is typically just a few volts. And so this high voltage here can create, the incredible high energy lightning bolts that we see during a thunderstorm. So for our last slide of this part of the video, I want to introduce a little tiny superhero named Battery Man. And Battery Man lives inside of every battery. So if you have a battery in your laptop computer, you have a battery in your phone, you have a battery in your flashlight, maybe a portable radio, whatever, right? So batteries are very common, and inside every battery is our imaginary little friend called Battery Man. Now, what is his job? Well, his job is to move charges from one end of the battery, the negative terminal, to the positive terminal of the battery. And you can see him doing that. He's doing a lot of work here, lifting up these charges, using this rope and this pulley system. So what happens here is as he raises these positive charges up here, they have higher potential energy when they're up here, and that relates to high voltage. So that's why we call this terminal positive. And these charges, these positive charges, we can think of them as flowing around the circuit here through the resistance, through the wire, and coming back in down here where they have lost all their energy. They're low potential energy now, and we're talking about electrical potential energy here, and therefore low voltage. So this is the minus end. And so Battery Man moves these charges and lifts them up so that they can keep flowing around and around in this circuit. All right, so you probably by now figured out that, well, there's not really a tiny little guy, Battery Man, living inside of this battery. However, what there is in here are electrochemical reactions that basically work just like Battery Man. The electrochemical reactions move these charges through the battery and allow the current to flow. So they create the voltage difference between the positive terminal and the negative terminal of the battery. Now, speaking of Battery Man, if we were just to keep him working in here and never feed him, obviously he's going to run out of energy, right? He's going to get very tired and sleepy. This is what happens to batteries. And batteries can be recharged. You can think of that like giving Battery Man a little break and giving him some food. So we, throw a sandwich in there, he eats that sandwich, now he's got more energy. So from an electrochemical standpoint, what happens is when you charge your phone or charge your computer, you are basically regenerating the electrochemical reactions in there and adding energy to them so that they can continue to work like Battery Man and moving the charges around in the circuit. So instead of drawing this complicated picture all the time, we abbreviate a battery. This is the symbol for a battery, and this is called the schematic symbol for a battery in an electric schematic diagram. A battery has a long line here which represents the positive terminal, and a short line which represents the negative terminal. So remember that current always flows from positive around in this direction, so it would be clockwise in this picture, and it comes back in the negative terminal of the battery. So this diagram here, we can now interpret this. We've got a battery over here with some voltage V. We've got current I flowing through this circuit, and this zigzag line over here represents a resistance in the circuit. So that's the end of part one. We're going to look at circuits in much more detail in part two, and we're going to start right where we left off here. So I will see you shortly in part two of this lecture.